Structural Steel Design by Engineer Francisco R. Onde Jr. Hello everyone, welcome back to my channel, and in this video we'll be discussing how to calculate the nominal compressive strength of a built-up section in accordance with NSCP 2015 specification, which is the same with the AISC specifications. Okay, this is the figure, or this is the built-up section that we're going to discuss. And also we'll be discussing the LRFD design compressive strength of the section and the ASD allowable compressive strength, considering flexural buckling only. And also, after getting those strengths, we're going to be calculating the safe service load the column can carry if there is a given service dead load. Okay, so without further ado, let's start na. But before it pala, if you haven't subscribed yet to my channel, please do so. Okay, so this is the question. Determine the nominal compressive strength of a built-up section consisting of W360 by 91 with two 12mm plates welded to form a back section based on the limit states of flexural buckling. The W shape and the plates have Fy equal to 248 megapascal. The section is used as a 10-meter long column and is fixed at both ends and braced at mid-height about the weak axis, or that is the y-axis. The section has no slender member. Use the recommended design effective length factors. And these are the properties of the W shape. Okay, and the length of that plate is the same with the depth of the W shape. Let's discuss this in details. It says that the section has no slender member, and that means we don't have to investigate if the width to thickness ratio of the members exceed the limiting width to thickness ratio. Okay, so let's go on determining if the buckling is inelastic or elastic. If that is inelastic, then we're going to use the formula FCR equal to 0.658 raised to Fy over Fe times the quantity of Fy. And if the column is elastic, then we're going to use FCR equal to 0.877 Fe. And that can be determined if KL over R exceeds 4.71 square root of E over Fy. So we need to calculate the KL over R. But the R is the radius of gyration of the built-up section, and not just the radius of gyration of the I shape. Okay, this is only for the I shape. So we have to calculate the area and the moments of inertia with respect to principal axis. Okay, let's start with the area, the total area or the gross area. The area of the steel is 11,500 and add twice of the area of the plate. So that is times 12 times 353. Okay, so we can get 19,972. That is the area of the plate. Okay, after that, calculate the moment of inertia with respect to x-axis, the principal axis. So this built-up section is a doubly symmetric section. That means they are both symmetrical in x and y. Okay, so that means the neutral axis is just located at the neutral axis of the I shape as well. They are collinear, or this principal axis of the built-up section pass through the centroid of this I shape or W shape. So we can directly calculate the IX by adding the IX of the I shape, that is 266 times 10 raised to 6 plus twice of the moment of inertia of this steel plate. And the moment of inertia of a rectangular section is BD cubed over 12. So the B is the width, 12. D is the 353 raised to 3 over 12. So that will give us 300, what is this? Let me just press N. And that is 353.97 times 10 raised to 6. Well, that is the moment of inertia of the built-up section in millimeter raised to 4 yan. Next, let's calculate for the Rx. The Rx is equal to square root of Ix over the total area. Okay, so that is equal to the square root of 353.97 times 10 raised to 6 over 19,972. And that will give us 133.13. Okay, so that is in millimeters. After that, let's calculate the Ry. But first, we've got to calculate I sub y, the moment of inertia with respect to this y-axis. And that is equal to the moment of inertia of this I shape with respect to y, Iy, plus the moment of inertia of these two plates with respect to this centroid or to this y-axis. So we have to add the AD squared. Okay, so this is equal to Iy 44.5 times 10 raised to 6 plus twice times the moment of inertia of this with respect to dito. So its centroidal moment of inertia is equal to 353 times 12 squared, 12 cubed over 12. But this is centroidal pa. No? We have to add the distance formula. So that is AD squared. So I mean transfer formula, AD squared. So that is 12 times 353 times the square of the distance of its centroid from the neutral axis, y-axis. So that is equal to the half of 254. Okay, so that is this, plus the half of this, 12 over 2. Okay, and this is square. So ganito yun, no? We are solving for this distance, okay, to the centroid here. Okay, so that is half of 254 and half of 12. So that is equal to this. And pressing N, that is 194.46. That is in millimeter to the fourth. So we can now calculate its Ry, the radius of gyration of the belt-up section. So it's 194.46 times 10 raised to 6 over the area, 19,972, and that gives us 98.67, okay, in millimeters. Let me write them here because we're gonna need them now to calculate for the KL over R. So let's go there. Let's calculate the slenderness ratios with respect to X and Y. Well, the limiting slenderness ratio for inelastic buckling is 4.71 square root of E over Fy. So, i-calculate muna natin yung actual KL over R. Now here, if we are considering the flexural buckling with respect to X, there's no effect. No, I mean, walang epekto yung lateral bracing dito. So we're gonna use this whole length as L, while K must be the recommended design value of K. We were asked not to use them, not the recommended design effective length factors. So theoretically, the value of K, if the ends are fixed, must be equal to 0.5. But since we're asked to get the recommended design, then we're gonna use K equal to 0.65, okay, for fixed at both ends. And of course, L is the total unbraced length with respect to X direction or X axis. So that is equal to 10 meters. So KL over R must be KL over RX, okay? So that is equal to 0.65 times 10,000 over this 133.13. And it gives us 48.82. Okay, that is the slenderness ratio with respect to X. Now, with respect to Y, so there is a lateral bracing, right, with respect to the weak axis or the Y axis. So that means its flexural buckling would be like this. Okay? So, since fixed yan dito, no, may ganyan yan. No. Now, here, the bracing must be considered like as a pin, okay? Because it's free to rotate here. It's not constrained from rotation. Dito, it's constrained from rotation. So, theoretically, the K that we must use is the same as here for fixed and pin. So that's supposedly 0.7, but since we're asked to use the design value, the recommended design value of K, then we're gonna use K equal to 0.8. And of course, the unbraced length here, L, is equal to half because this bracing is at the mid-height. So the total length is 10 meters, half of the length, that is 5 meters. So solving for KL over R, that must be equal to 0.8, the recommended K, times the unbraced length, 5,000, over RY, RY of the composite section. So that is, I mean the built-up section, that is 98.67. And that is 40.54. Now, among these two, we have to choose the maximum, and that is this 48.82. That means if this is the case, then the flexure or the flexural buckling occurs with respect to X axis first, before it occurs with respect to Y axis. So we're going to use this 48.82. Now let's calculate the limiting. Again, the limiting for inelastic buckling is 4.71 square root of E over Fy. And that means if the KL over R exceeds this, then the buckling will be elastic buckling. Okay? But if KL over R is less than this, then the buckling is an inelastic buckling. And that is more safer than elastic buckling. So 4.71 square root of 200,000 over 248, okay, that is 133.76. And again, the KL over R is 48.82. And this is less than this. Okay? So that means the kind of buckling is an inelastic buckling. For inelastic buckling, we're going to use the formula FCR is equal to 0.658 Fy over Fe times Fy based on the code. Now, so Fe is the elastic critical buckling, or also called as the Euler buckling stress. So that has a formula Fe is equal to pi squared E over KL over R squared. And substituting that, this is equal to pi squared times 200,000 over that 48.82 squared. And that is 828.2. Okay, that is the value of Fe. Now, after that, we can now calculate the flexural critical buckling stress, and that is FCR equal to this. Again, if this value exceeds this, suppose, then we must not use this. Instead, we must use the elastic buckling states or stress that is equal to 0.877 of Fe. Ganyan. But since this is an inelastic buckling, then we're gonna use this. Okay? So 0.65 raised to E, I raised to Fy, 0.65 8 raised to Fy 248 over Fe 828.2 times Fy, which is 248, and that will give us 218.79, okay, in megapascal. That is the flexural critical buckling stress. So with that, we can now calculate the nominal strength Now that's what's being asked in this problem. So the nominal compressive strength is of course just the product of FCR and the gross area. Okay, that should be the total area of this built-up section. And that is equal to this FCR, 218.79, times the area. The gross area is equal to 19,972. And that is equal to this, 4,369,673.88 in newtons. But in kilonewton, that is 4,369.67 kilonewton. So this is the answer for this question. Okay, so it's easy lang. Now, what if the question is, what is the LRFD design compressive strength of this built-up section? So here, we just have to calculate phi Pn. We just have to multiply the strength reduction factor phi with Pn. And for compression, phi is 0.9. So multiplying this by 0.9, that will give us 3,932.7. Okay? Now, what if the question is, what is the ASD, allowable compressive strength? So if this is the question, we just have to divide this Pn by the factor of safety. The factor of safety is just equal to 1.67. Okay, so dividing it by 1.67, the quotient is this. This is the allowable compressive strength for ASD, 2616.57. Now, if we are to compare this, if we are to solve this using the 2001 NSCP code or the previous code in AISC, which has a formula of 1 minus 1/2 KL over R over CC squared times Fy over Fs, okay, which Fs is equal to 5/3 plus 3/8 of KL over RCC minus 1/8 of the cube of KL over R over CC. Then we're gonna calculate this. Now if we are to calculate that using 2001 NSCP. So they are much close lang. Now they are just close. Okay. So ganun yan. Now, what if there is an additional question? No, upon having this, nakuha na natin yung mga nominal strength, LRFD design compressive strength, and also ASD allowable compressive strength. What if this is the question? What is the safe service load if the service dead load is 630 kilonewton? This is compressive load. What is the safe service compressive axial load, axial live load, that this column can carry if the service compressive axial dead load is 630 kilonewton? These loads must be axial. Okay, that means these loads act at the centroid. Okay, so ganun yan, or the axis of the longitudinal direction of the column. So calculating for the service live load using LRFD, we know that phi Pn, the design compressive strength, must be greater than the required strength. No, required strength, which are factored 1.2 PD plus 1.6 PL. So that PL must be less than phi Pn minus 1.2 PD all over 1.6. So doing substitution, we got phi Pn in the previous slide equal to 3,932.7, and the given dead load is 630 kilonewton divided by the factor 1.6. So that will give us 1,985.44. Now the live load must be less than that, okay, considering LRFD. And if we are to consider ASD, so we know that the the ASD allowable compressive strength Pn over omega C must be greater than the sum of the live load and the axial dead load without factors. So if we're to calculate the live load, it's just the difference. The safe live load is just a difference of this allowable minus the service dead load. So we got in the previous slide this being equal to 2,616.57 minus 630, and that will give us 1,987.57 kilo Newton. So as you can see, malapit lang sila. Na minsan, nalayo sila. No? So suppose, if nalayo sila, let's say may difference to 100, better to choose the minimum. Of course, you must choose the minimum. Now if you are considering both, okay? So ganun yan. Well, if this would be a problem in board exam, say the choices are 1,000, 1,500, 1,900, 2,000. So the greatest safest live load that it can carry is 1,900, considering among the choices. Okay? So ganun yan. Okay, so thank you for listening. By the way pala, no, for this type of section, this may not just fail using the flexural buckling or on the limit state of flexural buckling. This could also fail in torsional buckling. No, but since we're just asked to determine the limit states or the nominal compressive strength, considering the limit states of flexural buckling, that's why we only use that formula. No, ganon. Okay. Okay. So thank you for listening. I hope may na-learn kayo. No, like this video if nagustuhan ninyo, and also share this to your friends, share this to your classmates, no, future engineers. Okay, and also comment if you have any suggestion or if you have problem that you want me to solve. Okay, just comment in the comment section, and also do not forget to subscribe in this channel. Okay, so thank you for listening. By the way, we have a Facebook group of which I am posting the PDF copies of the handouts or of this problem. So look for the Facebook group on the real subscribers. Okay, on the real solution subscribers. So see you there. Thank you for listening. Goodbye and God bless.